All right, let's look at the moments of inertia. All right, moment of inertia of mass m can be found by, mass m times L is the distance from the center of the circular motion squared. All right, so where did that come from? All right. So probably the easiest way to look at to explain that would be looking at the kinetic energy. So let's say you have a mass m, going in a circle with radius L, right? And so if you want to find the kinetic energy of that mass would be K. I'm going to use K for kinetic energy is equal to, and 1/2 m times velocity squared, right? We've seen that in physics class, right? And so in a circular motion, linear velocity v can be rewritten as v is going to be equal to, actually, I'm going to use red here. V is equal to, right? The radius, which is going to be L, right? Times the rate of change of the angle, so you have a d theta over dt, just a derivative of the angle theta, right? So if you plug this guy into the kinetic energy formula, you will get this, 1/2 m, and velocity is just L times d theta over dt squared, right? So if you multiply that out, you're going to end up getting 1/2, right? Then you have ml squared d theta over dt squared, right? So if you compare this to the original kinetic energy formula here, so this is the original kinetic energy formula, and this is what we got here, right? Then it's got the very similar format, and you can see the correspondence, especially we're looking at in a linear motion, m was the mass, right? In a circular motion, the mass has a different effect depending on how far it is away from the center of the circular motion. If you are far away from the center, the mass is going to have a larger effect. If mass is closer to the center, the mass have a smaller effect. So to take that distance into consideration, we can see that this is going to be equivalent, or it corresponds to the mass in a circular motion there. So that is the moment of inertia. So this guy right here is the moment of inertia, right? So this is kind of like the mass in a circular motion, right? That's where moment of inertia comes from, right? Then what we want to do is let's look at the two-dimensional case and try to find the moment of inertia of like two-dimensional plates or metal plates or something like that, rotate about the x-axis and y-axis and the z-axis, right? So let's look at the moment of inertia. Moment of inertia. Oh, actually, inertia about the axes, right? So if you want to find the moment of inertia, say I, about the x-axis, right? So obviously, since you have a two-dimensional plate and the density might be different, so we're going to look at the integral here, right? So I'm going to use here dm. So this is a mass element, right? And then mass element times distance squared. So in this case, this is rotated about the x-axis. The distance is determined by the y-coordinate. So you have a y squared. and then you're going to integrate it over this region R. So this is going to give us the moment of inertia about the x-axis. And in a similar fashion, we can find moment of inertia about the x-axis, y-axis. Right? Of course, we have integral over the same region R. Then this is a mass element. Right? Then if you're rotating about the y-axis, so you take this plate and spin it around the y-axis, the distance is determined by the x-coordinate of the point. So we're going to use x squared. Right? And then if you rotate it about the z-axis, so I sub z is going to be an integral over the same region, and there's a mass element. Right, but the distance is determined by square root of x squared plus y squared. So square that, you're just going to end up with x squared plus y squared. Right, so that's the moment of inertia about the z-axis. And you can see that by looking at the formula, I sub x plus I sub y is going to end up with I sub z. This is called the perpendicular axis theorem. So I'm going to just write that down. This is called the perpendicular axis theorem, which basically states what I've just said. I sub x plus I sub y is equal to I sub z. Right? So this is called the perpendicular axis theorem. Right? There's something called the parallel axis theorem. Right? So I'm going to introduce, let's see, IM. So let's see, I sub m. Right, this is the moment, if I can spell moment, moment of inertia through about the axis through the center of mass. Let's say x bar comma y bar, and it's perpendicular to maybe I should say parallel to the z-axis. All right. So what happens is here, if you have say I'm going to just put the random point. Let's say this happens to be the center of mass, right? Then axis that we're talking about is going through here, right? So if you rotate about that axis, it's called the moment of inertia, I sub m, right? Then there's another theorem is called parallel axis theorem. So this is called parallel axis theorem, right? Which states this, right? The moment of inertia so moment of inertia I about any axis parallel to z-axis is always going to be this Im. So which is going to give you the smallest possible moment of inertia about the axis, parallel to z-axis, plus m, the total mass, times the distance between those two axes squared. So if you have a region right there, so let's see, then axis happens to be here. All right, so the axis should say axis is going to be just a random axis, right, like here. So let's say this is the random axis. Then we want to find the moment of inertia about that axis, right? So this is parallel to z-axis, right? The distance d is determined by just finding the distance between these two guys right here. So distance from here to there, right? So this is d, right? So the parallel axiom theorem says that the moment of inertia about this axis here is going to be a moment of inertia about the axis through the moment of a center of mass plus total mass times this distance squared, right? So that's what the parallel axiom here, right? So what I'm going to do next, in the next video, I'm going to try to prove the parallel axis theorem, right? That's it. I hope that this was clear.